Hello everyone, welcome to another session of Class 12 Mathematics. I am Deepa, faculty at Silver Hills Public School. Today we will be discussing the topic probability from Class 12 CBSE. So before we move to the topic, let's discuss some of the terms that we use in probability. So tell me children, what do you mean by a random experiment? An experiment whose outcome is unpredictable is called a random experiment. Now we cannot predict what the answer will be. Not only that, more than one answer can come in the case of a random experiment. So the common experiments like tossing a coin, rolling a die, all these are examples for random experiment. Now another term associated with this is sample space. Now children, tell me, what do you mean by a sample space? Sample space is the collection of all outcomes of the random experiment. And what is a letter to denote that? Usually we denote S, the letter S for sample space. Then comes the definition event. What is an event? An event is a subset of a sample space. So if we collect some results of the sample space, that collection is called an event. And remember, event is always a subset of a sample space. So these are some of the terms that is associated to probability. So we will be discussing a new topic, that is conditional probability. And let's see what it is. So let's begin with a question. Suppose you have an experiment, say the random experiment is you are rolling a die. So what are the members, what are the outcomes of this experiment? I can write S is equal to, what is this S? S denotes the sample space. S is equal to set 1, 2, 3, 4, 5, 6. 6 outcomes are there. Now I am going to define an event E. What is my event E? Event E is getting an even number when you roll a die. And I am going to define another event, say F. And what is this F? F is getting a number greater than 4. So once again, E is even, getting an even number when you roll a die. And the second one is F. The event F is getting a number greater than 4 when you roll a die. So let's list the members of E and F. So what are the members of E? I can write E is equal to set, what are the even numbers coming here? Set 2, 4, 6. And what is F? I can list the members of F. F means getting a number greater than 4. So what are the numbers available here? We have 5 and we have 6. So I have two events E and F. Now I want to find probability of E. What does that mean? What is the probability of getting an even number when you roll a die? Now all these outcomes have the same probability, 1 by 6, 1 by 6, etc. So to find the probability of an event, what will we do? We will divide the number of members in E by the total number of members in S. So how many members are there in E? You have 3. By how many members are there in S? You have 6. So your answer is 1 by 2. So probability of getting an even number is 1 by 2. Now I am going to change my question. Suppose I change my question to find the probability of getting an even number if the die shows a number greater than 4. What is it? The question is, what is the probability of getting an even number when you roll a die if the die shows a number greater than 4? So there is some additional information here. What is it? I know that the number that comes on the die will be greater than 4. So will be greater than 4 means what are the possibilities here? We have 1, 2, 3, 4, 5, 6, but we are not bothered about the first 4 numbers because I know the number is greater than 4. So I have 5 and 6. And the question is, what is the probability of getting an even number from here? See, 2 members are there in total and you have just 1 member here, 1 even number, that is 6. So, if my question is presented like that, probability of getting an even number E, because E I have already taken as getting an even number, but then I change the question, what is the probability of getting an even number if the die shows a number greater than 4? So, the probability will be 1 by 2. Such a probability where we apply a condition is called conditional probability. So here we are going to find probability of getting an even number, and what is the condition here? I know the number on the die is greater than 4. Such a probability is called conditional probability, and let's see what is the definition of conditional probability and what is the formula to find the conditional probability of an event. Now if I take the same experiment and if I represent this in a Venn diagram, how does it look like? Let's see. This is S, sample space, and I have 2 events here. One is E, the other one is F. E was getting an even number. So I have 2, 4, I have 6, and F, the event F was getting a number greater than 4. So getting a number greater than 4 means I can include 5 and 6. Already 6 is there, which is common to both, and I wrote 5 here. Now few more elements are there. I can write 1 here, and then what is left? 3. Okay, this is a diagram. Now I want to find the probability of getting an even number under the condition that I know the condition, the die shows a number greater than 4, and we got the answer, that is probability of event E, okay, under the condition F, which will be denoted by this symbol, and we read it as probability of E given F has taken place. That is probability of getting an even number given a number greater than 4 has appeared on the die, and we got the answer as 1 by 2. So how can we derive a formula for this? Now check this. When I consider P of E given F, that is probability of E given F has taken place, I just concentrate on F. F means the thing that which we know. What we know, the number is greater than 4. So how many members are there? 2 members. Okay. So that comes in the denominator. That means the number of elements in F comes in the denominator. And see what comes on top. From F, which is the even number present there, only 6 is present. And where is this 6 present? It is in the intersection region of E and F. So I can write N of E intersection F by N of F. So only one member is there in E intersection F, that's how I got 1. And how many members are there in F? 2. Now this expression, if I divide the numerator and denominator with the number of elements in the sample space, I am just dividing the numerator and denominator with N of S. So what happens to the result? This is actually probability of E intersection F by. So when you combine these two, you get probability of F. So we got the definition of P of E given F, that is a conditional probability. What is the definition? P P of E given F is equal to probability of E intersection F divided by probability of F. Now one more condition is there. What is it? Denominator not equal to 0. Okay. So if you get any question, select E as the event that you are going to find, and what will be F? Something that which we know, the event that we know, that we will select as F, and just apply this result, you get the answer. Okay. So this is a definition. Conditional probability, if E and F are two events, then probability of E given F. So whatever event you write in the denominator, that has already happened. This is equal to probability of E intersection F by P of F. Condition P of F not equal to 0. Now there are some properties related to conditional probability. Three main properties are there. Let's see how we can prove these. Look at the first property. What is said here? Probability of S given F is equal to probability of F given F is equal to 1. What is S here? S is a sample space. Now let's check, children, how we can prove this result. The first result, probability of S given F. We just apply the definition of conditional probability. P of E given F was P of E intersection F by P of F. Same way, I just apply P of S intersection F divided by the event in the denominator is F. So P of F, that is equal to, now S is a sample space, F is a subset of S. So when you find the intersection, naturally the answer will be, it will be P of F, because F is a subset of S. F is a smaller set when compared to S, by P of F. So your answer is 1. Same way I can prove the next one also. P of F given F. By definition it is P of F intersection F divided by P of F. Now any set intersection, the same set is the same set itself. So P of F divided by P of F, that is equal to 1. Okay. So we proved the first condition, P of S given F is equal to P of F given F is equal to 1. Now look at the second one. If A and B are two events, and if F is any event of S such that probability of F is not equal to 0, see we have a lengthy formula here. What is it? P of A union B given F is equal to P of A given F plus P of B given F minus P of A intersection B given F. Now let's see how to prove it. This was the first one, first property. Coming to the second property. P of A union B given F is equal to, here in the numerator you have A union B and denominator it is F, that is the only difference. So this is equal to P of A union B, okay, club it together, intersection, the event in the denominator, intersection F divided by probability of F, that is equal to. Now just apply the distributive property, just open the bracket. So we get P of A intersection F union B intersection F divided by P of F. Okay. Now this you can treat it as one event, this another event. So children, what is the formula of P of A union B? If A and B are two events, it is P of A plus P of B minus P of A intersection B. Here instead of A you have A intersection F, and instead of B you have B intersection F, that is the only difference. So we just apply the result there. This is equal to P of the first one plus P of the second one, probability of B intersection F minus P of, it's A intersection F intersection B intersection F. What is it? A intersection F intersection B intersection F. Here two things are coming, which will take it as one. So this I can write as A intersection B intersection F. So I'll just copy it here, minus A intersection B intersection F divided by P of F. Now we divide each term with probability of F, that is equal to P of A intersection F by P of F plus P of B intersection F by P of F minus P of A intersection B intersection F divided by P of F. Okay, so we reached here. Now look at this. What is this? This is actually a conditional probability. This is equal to P of A given F. Just think in the reverse order. P of any event given F is equal to P of A intersection F by P of F. So it's correct. Plus this is P of B given F minus. Now here what will we write? This is P of A intersection B given F. So we proved that. What did we prove? P of A union B given F is equal to P of A given F plus P of B given F minus P of A intersection B given F. Now children, suppose A intersection B is 5. That is, if A and B are disjoint, intersection is empty. A intersection B is 5. So what happens to probability? The probability becomes 0. So that means if A intersection B is empty, the whole thing, this part becomes 0. So you will be left with just two terms, that is P of A given F plus P of B given F. That means suppose A intersection B is equal to 5. So we get P of A intersection B given F. It becomes 0. Okay, so our formula get reduced to P of A union B given F is modified as P of A given F plus P of B given F. The remaining portion won't be there because it is 0. So when can we apply this result? If A and B are disjoint. Nothing is common in A and B. So that is the second result. If A and B are two events and if F is any event of S such that probability of F not equal to 0, then P of A union B given F is equal to P of A given F plus P of B given F minus P of A intersection B given F. Now if A and B are disjoint, then what happens? It gets reduced to just two terms. Answer will have just two terms, that is P of A given F plus P of B given F. Hope that is clear. And then one more property, that is probability of E complement given F is same as 1 minus probability of E given F. Now let's see how we can prove that part. That is a third one. Probability of E complement given F is equal to 1 minus P of E given F. This is what we need to prove. So now children, what is the relation connecting an event and its complement? Suppose I have an event E and its complement is E complement. So E union E complement is equal to, what is it? It is a sample space S. and E intersection E complement is equal to 5, because nothing is common in an event and its complement. So, E intersection E complement is equal to 5, or in other words, E and E complement are disjoint. Now, first property says probability of S given any event F is equal to 1, where S is a sample space. Now, instead of this S, I can give this. Instead of S, I can write E union E complement. So, I modify this as E union E complement given F is equal to 1. Now, E and E complement are disjoint. So, think of the second property. If A and B are disjoint, probability of A union B given F is equal to probability of A given F plus probability of B given F. So, in the place of A you have E, and in the place of B you have E complement. So, we are just applying that property. So, I modify this as P of E given F plus P of E complement given F is equal to 1. Now, we almost got the answer. From here, I can write P of E complement given F is equal to 1 minus P of E given F, and that was the third property. These are three simple results which you can apply in problems. When problems comes based on these results, you can use it. Okay. So, that is these are the properties based on conditional probability, conditional probability. So, definition of conditional probability, the formula, and these simple properties you keep in mind. Now, let us move to the problems. The first problem is, if P of A is equal to 7 by 13, P of B is equal to 9 by 13 and P of A intersection B is 4 by 13, evaluate P of A given B. It's a very direct question. If you know the formula, you can just apply these values and you will get the answer. This can come either for 1 mark, it can be a 1 mark question, or like 2 mark questions can come where it has got subdivisions. Here it's just one question, find P of A given B. Whatever it is, we'll just find out. P of A given B. By definition, it is P of A intersection B divided by P of B. That's equal to. Now, all the values are available here. Just substitute that. You get 4 by 13 divided by, and what comes in the denominator? P of B. You have 9 by 13. 13 get cancelled and your answer is 4 by 9. Okay. Next one. A family has 2 children. What is the probability that both the children are boys, given that at least one of them is a boy? Here the numbers, the probabilities are not given directly, it is in the form of a statement sum. So, anyway, we got an idea this is based on conditional probability. Why? Check the last sentence. What is the probability that both the children are boys, given that? Okay, so given that means some condition is given here. So, we need to select an event E, event F. Okay, event F means something which we know, and then we can apply P of E given F, the formula. So, a family has 2 children. So, what are the members of the sample space here? 2 children means it can be like both can be boys. One is a boy, the other one is, first one is a boy, second one is a girl, that can happen. GB can happen, and then you have both girls. These are the possibilities. A family has 2 children. So, these are the possibilities, outcomes. So, now I am going to define an event E and an event F. What is event E? The probability of what? What are we going to find? What is the probability that both the children are boys? So, E is an event both the children are boys. And what is F? F is something which we know. See the last sentence, given that at least one of them is a boy. So, at least one of them is a boy. So, what do you mean by at least one? One or more than that? Okay. So, now let us list the members of E. What are the members of E? Both the children are boys. So, what will come here? B. And what about F? At least one of them is a boy. One boy should be present, at least one. So, it can be this. 3 outcomes can come. So, F is equal to BB, BG, GB. So, if you are applying the formula, definitely we need E intersection F. So, let us find E intersection F. What is E intersection F? Only one member is common, B. Okay. Now, coming to the definition, P of E given F is equal to P of E intersection F divided by P of F. Now, we are going to find the probabilities. E intersection F is ready. How many members are there? 1. So, what will be P of E intersection F? Total outcomes, it is 4 actually. So, 1 divided by 4 by, what is probability of F? 3 members are there out of this 4. So, 3 divided by 4. 4 and 4 get cancelled and your answer is 1 by 3. You can use a formula. Without using the formula also you will get the answer. Now, you know the condition is at least one of them is a boy. If so, we will fix that. This is your event, at least one of them is a boy. From here, what is the probability of getting E? You can think like that. So, from here, what is the probability of getting E? 1 out of total 3. So, directly you get the answer 1 by 3. So, remember children, conditional probability means we are just reducing the sample space. In this case, the sample space becomes F. If we do not use a formula, sample space becomes F. That is 3 members are there and 1 out of 3. But here we applied the formula and we found the answer as 1 by 3. Next one. 10 cards numbered 1 to 10 are placed in a box mixed up thoroughly and then one card is drawn randomly. If it is known that the number on the drawn card is more than 3, what is the probability that it is an even number? Again here one condition is given and we are going to find what is the probability that we get an even number. So, select one event E and select one event F. So, what is the event E? The probability of getting an even number. So, let us select getting an even number as event E. And what is F? See, something which we know. If it is known that the number on the drawn card is more than 3. So, number on the card is greater than 3. This is what we know. Now, we need to find P of E given F. Okay. So, by definition, P of E given F is equal to P of E intersection F divided by P of F. Now, first event is getting an even number. So, cards numbered from 1 to 10. So, how many even numbers will come there? You have 2, 4, 6, 8, 10 10. 2, you have 2, 4, 6, 8 and 10. Second one, number on the card is greater than 3. So, greater than 3 means 3 is not included. 4, 5, 6, 7, 8, 9, 10. And then we need E intersection F anyway. So, E intersection F means how many members will be there? You have 4, you have 6, you have 8, 10. So, 4, 6, 8 and 10. Members are ready. Now, let us fill. P of E intersection F. Total 10 cards are there. Of that 4. So, 4 by 10 divided by. Now, what is probability of F? How many members are there? 1, 2, 3, 4, 5, 6, 7 members are there. 7 by 10. So, your answer is 4 by 7. Okay? 4 by 7. Next one. In a school, there are 1000 students, out of which 430 are girls. It is known that out of 430, 10% of the girls study in class 12. What is the probability that a student chosen randomly studies in class 12 given that the chosen student is a girl? So, we are going to find a probability of an event given one condition. So, definitely we need to apply conditional probability. So, let us select the events E and F. So, what are we going to find? What is the probability that a student chosen randomly studies in class 12? So, event E is the student is from which class? Class 12. And what is F? F means something which we know. What is it? Given that the chosen student is a girl. Okay, the chosen student is a girl. So, 2 events are ready. And then we are going to find P of E given F. That is equal to, by definition, P of E intersection F divided by P of F. Condition P of F not equal to 0. Now, we are going to find each probability. F is even, the chosen student is a girl. So, let us see what is P of F then. In a school, there are 1000 students. 1000 students are there, out of which 430 are girls. And see, our event F is the chosen student is a girl. So, probability of getting a girl child, that what is it? 430 by total number of outcomes. Out of 1000, 430 are girls. So, 430 by 1000. Okay, we will write that. That is probability of F. Denominator is ready. And then we need probability of E intersection F. What is the meaning of that? E is the student is from class 12. F is the chosen student is a girl. So, E intersection F means that the student that you selected is a girl. So, probability that the student is a girl from class 12. How do we find? See, look at the sentence. 10% of the girls study in class 12. Like 430 students are there, 430 girls are there out of 1000. Of that, 10% of the girls study in class 12. So, how do you find P of E intersection F? This is equal to 10% of 430. So, 10% of 430 by the total sample space, that is by 1000. That is equal to 10% means 10 by 100 into 430 divided by 1000. That is equal to 43 divided by 1000. Okay, no need to cancel all these here, like finally those terms, those numbers get cancelled. So, this is equal to, now the values are ready, P of E intersection F is 43 divided by 1000, and P of F, it's ready here, it is 430 divided by 1000. 1000 and 1000 goes, you get 43 by 430, which is 1 by 10, and that is 0.1. Okay. 43 by 430, 1 by 10, 0.1. That is a required probability. So, select one E, one F, which has already happened, and then just apply the formula. Hope that is clear. This is also a simple question. And now, a die is thrown 3 times. Events A and B are defined as below. A is 4 on the third throw, B is 6 on the first and 5 on the second throw. Find P of A given B. Okay. So, events are given here A and B. We need not select the events from the statement. We just have to find P of A given B. Now, what is our experiment? A die is thrown how many times? 3 times. So, total number of outcomes. How many outcomes will be there? If you roll a die once, 6. So, if it is 2 times, 6 square. So, 3 times means it is 6 cube. You have 216 outcomes. Okay. We do not want to list all the members. We just want the number 216. Now, let us see the first event A. 4 on the third throw. So, what will be the members? We need not list all the members, just we will write 4 on the third throw means the first 2 position can be any number, but the third number, third time definitely a 4 comes. So, your members can be like 1, 1, 4, it can be 1, 2, 4, okay, dot, 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 it goes. And then you can list all the members such a way that the last number is just 4. And you can write 614, 624, etc., etc. It can be 664. Okay, members are there. Now, what is B? How do we list the members of B? 6 on the first, 5 on the second throw. First 2 positions are fixed. The first one is occupied by 6, second one by 5. Third place can be any one of those 6, like 1, 2, 3, 4, 5, 6. So, B, the members of B can be written as 6, 5, 1, because first 2 places are fixed. Second one, it is 6, 5, 2, 6, 5, 3, 6, 5, 4, and then you have 6, 5, 5, and finally 6, 5, 6. These are the members of B. Question is find P of A given B. So, I need P of A intersection B and P of B also. So, now will I just find A intersection B? What are the members common to A and B? A intersection B means, what does that mean? 4 must be present on the third throw, and what is B? 6 on the first, 5 on the second. So, when we read it together, what is it? 6 should come on the first throw, 5 on the second throw, and 4 on the third throw. So, how many members will be there? Just one member, right? And which is that member? That is 6 on the first throw, 5 on the second, and 4. So, it will be 6, 5, 4. This is a member common to these two. So, I will write 6, 5, 4. So, A intersection B has just one single member. So, we will apply the result. P of A given B is equal to P of A intersection B divided by P of B. Now, see, A intersection B has just one member out of 216, because number of members in the sample space is 216. So, I will write 1, by 216 divided by, now what is probability of B? How many members are there in B? 6 members out of the total 216. 6 by 216. So 216 get cancelled and your answer is 1 by 6. Okay. A intersection B, and then we applied the formula. Next one. A die is thrown twice and the sum of the numbers appearing is observed to be 6. 2 times we are throwing a die, and what are we observing? We observe that the sum of the numbers appearing is observed to be 6. What is a conditional probability that the number 4 has appeared at least once? So once again, what is given here? The sum of the number appearing is observed to be 6. So this is what we know. On the die, the sum of the number is 6. And we need to find what is a conditional probability that the number 4 has appeared at least once. So that is our event E. So we will write event E is 4 has appeared at least once. And the event F which we know is sum is 6. Sum of the numbers that comes on the die is 6. So when we list the members, what are the members of E? 4 has appeared at least once. So I can write 4-1, 4-2, 4-3, 4-4, 4-5, 4-6. And then the reverse order also I can write. That is 1-4, 2-4, 3-4. Now 4-4 anyway we wrote, so we are not including that again. And then we have 5-4 and then 6-4 over. F. What are the members of F? The sum is 6. So which all numbers when you add gives the answer 6. So if I take 1, I know 1, 5. 1 plus 5 is 6. So I just take the reverse thing also. 5, 1. 5 on the first die, 1 on the second die. Yes. Now if I go for 2, 2 plus what gives 6? 2, 4 I can include, 4, 2 I can include. Okay, then coming to 3. 3, 3 gives you the answer 6. Any more elements here? No. If I take 4, again I get 4, 2. So these are the members. So how many members are here? You have 5 outcomes in F, and in E, how many members are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 members are there in E. Now we just take the intersection of these two. What are the members common to E and F? That means sum should be 6 and at least once the 4 should be present. So I get these two, right? Only 2 members are there. So E intersection F includes 2, 4 and 4, 2. Now we just apply the formula. P of E given F is equal to P of E intersection F divided by P of F. That's equal to. Now, E intersection how many members are there in E intersection F? Just 2 members. Out of total 36, because a die is thrown how many times? Twice. So I get 2 by 36 divided by probability of F. How many members are there? 5 members are there in F out of the total 36. 36 get cancelled and you get 2 by 5. So the answer is 2 by 5, and that is a conditional probability that the number 4 has appeared at least once. And what was the given condition? Sum of the numbers on the die, on both the dice, it was 6. Okay. And one more we'll do based on conditional probability, which is totally different when compared to the previous questions. Consider the experiment of tossing a coin. If the coin shows head, toss it again. But if it shows tail, then throw a die. Find the conditional probability of the event that the die shows a number greater than 4 given that there is at least one tail. There is at least one tail. So let's see, let's visualize this experiment. You have a coin, we are tossing a coin. So when you have a coin, what are the possibilities? Either head comes or tail comes, right? Now what is written here? If the coin shows head, you are tossing it again, toss it once again. So then you have head or you have tail. Now if it shows tail, then what happens? Then throw a die. So that means you have 1, 2, 3, 4, 5, 6. So when you combine these two, I can write the sample space S is equal to, what are the members here? You have HH, HT, okay, then you have T1, T2, T3, T4, T5, T6. Okay, either you can write H comma H in ordered pair, or even if you write H's, it's correct. Okay, if you want, you can write in terms of ordered pair. These are the members of the sample space. Now, what about the probabilities of each outcome? Are they same? Now, in the experiment, like if I roll a die, we know S is equal to 1, 2, 3 up to 6. Now in the first example which we did, what is the probability of an even number? What did we do? Like I know each outcome has same probability 1 by 6. So to find the probability of an event, what did we do? We just found the number of members present in the event by total number of outcomes, total number of elements in the sample space. That is what we did to find the probability. But here we can't do that because the probability varies. In that case, how do we find the probability of an event? We add probability of each outcome, each member present in the event. Okay, that is what we are going to do here. Now, if I take this one, HH, so if I combine this, I get HH, right? HH I get, HT I get, T1, T2, T3, T4, T5, T6. What is the probability of head? It is 1 by 4. How did you get that? 1 by 2 into 1 by 2, you will get 1 by 4. Again, probability of HT, it is 1 by 2 into 1 by 2, 1 by 4. Now coming to T1, probability of getting a tail is 1 by 2 when you flip a coin, and probability of getting a 1 when you roll a die is 1 by 6. So here the probability will be 1 by 2 into 1 by 6, that is 1 by 12. Now same for the remaining 1 by 12, 1 by 12, 1 by 12, 1 by 12. So if you consider these probabilities, they are not same. Okay, they are not same, they are different. Some like 1 by 12 is there, 1 by 4 is also included there. So we will have to find A, we will have to list the members of A and B separately, and then we need to add each probability, the probability of each member present in the event. So now let's list what is A and what is B. Event A. What is event A? Find the conditional probability of the event that the die shows a number greater than 4. So A is die shows a number greater than 4, and B is, what is event B? B is given that there is at least one tail. So given that means it is something event which we know. There is at least one tail. At least one tail appears. That is B. Okay. Now let's list the members of A and B. What are the members of A? Die shows a number greater than 4. So, greater than 4 means I can take only these two cases. One is T5 and the other one is T6. Okay? T5, T6. And what is event B? At least one tail appears. So, we just select those members that contains tail. This I cannot, this I can, and then the remaining all members contains tail. So, I can select all these members. So, if I list the members, I get HT. The first member is HT. The next member is T1, T2, T3, T4, T5 and T6. Okay. A ready, B is also ready. Now let us find A intersection B. So what is A intersection B? The elements common in both. So what are the elements common to both? It is T5 and T6. These are the elements common. Now let us find P of A given B. By definition it is P of A intersection B divided by P of B. Now let us find out P of A intersection B. P of A intersection B is equal to, there are two members, we are going to find the probability of each. This is same as probability of first member plus probability of second member. We know probability of T5, already we wrote all the probabilities there. Probability of T5 is 1 by 12. Okay, and T6 is also 1 by 12. So, I get 1 by 12 plus 1 by 12, that is 2 by 12, which is 1 by 6. P of A intersection B is ready. Now, what we need to find? P of B. What is the probability of B? So many members are there, we are going to add the probability of each. So, probability of HT plus probability of T1 plus T2 plus probability of T3 plus probability of T4 plus T5 plus probability of T6. All these we are going to add. First one's probability is 1 by 4. Now, for the remaining, the probability is 1 by 12. So, we get 1 by 12 plus 1 by 12 like that. So, how many 1 by 12 will come? You will be getting 6 outcomes are there. Now, 6 into 1 by 12, that is 1 by 2. Okay, when you add all these, 6 times 1 by 12 comes. So, what is 1 by 4 plus 1 by 2? You get 3 by 4. That is also ready. Now, we just substitute in the formula. This is equal to P of A intersection B is 1 by 6 by P of B divided by 3 by 4. That is 1 by 6 into 4 by 3. The answer is 2 divided by 9. Okay, you get the answer as 2 by 9. So, next question. If P of A is equal to 6 by 11, P of B is equal to 5 by 11 and P of A union B is equal to 7 by 11, find first one P of A intersection B, P of A given B and P of B given A. It is a very direct question. Let us see. P of A is given, P of B is given, P of A union B is also given. And children, what is the formula of P of A union B? P of A plus P of B minus P of A intersection B. Okay. So, given, we will do the first one. P of A union B is given as 7 by 11 and the formula is P of A plus P of B minus P of A intersection B is equal to 7 by 11. From there, it is easy to find P of A intersection B. Now, we just substitute what is P of A? P of A is equal to 6 by 11 plus P of B, that is 5 by 11. minus P of A intersection B, that we don't know, minus P of A intersection B is equal to 7 by 11. So, if you shift this to the other side, you get 6 by 11 plus 5 by 11 minus 7 by 11 is equal to P of A intersection B, and that is equal to 4 by 11. 4 by 11 is equal to P of A intersection B. 11 minus 7, you get 4. So, the answer is 4 by 11. So, the first part is done. P of A intersection B is ready. Now, let us evaluate the second part. The second one is P of A given B. Just direct formula. P of A intersection B divided by P of B. Now, what is P of A intersection B? It is there. It is available here. It is 4 by 11 by P of B. Now, P of B is 5 by 11. So, your answer is 4 by 5. Now, third one. The third one is P of B given A. So, on top B comes and A comes in the denominator. So, it is P of B intersection A divided by P of A. Now, A intersection B and B intersection A, they are both same. So, this is equal to, now A intersection B, already we know it is 4 by 11. So, 4 by 11 divided by P of A. Where is P of A? It is 6 by 11. So, your answer is 4 by 6. Now, if you simplify further, it is 2 by 3. Okay. So, these are the answers. Next one, mother, father and son line up at random for a family picture. Now, two events are given here. E is the event, son on one end, F is the event, father in the middle. Find P of E given F. The events are listed here, E and F are given here. So, how do we find P of E given F? So, now they are mother, father and son. They are going to take a picture. So, how can we arrange them? Suppose father is in the middle, then mother, son, son, mother. Okay. Now, mother is in the middle, father, son, son, father. And then son is in the middle, mother, father, father, mother. So, these are the 6 possible outcomes. So, they can stand for a photo in these positions. Now, let's take the event E. Event E is given here, son on one end. So, what are the members? Son on one end means I can take this, I can take this. These 4 I can include. So, M, Fs, SFM, FMS, son, mother, father. These members I can include. Now, F is the event, father is in the middle. So, father is in the middle means these 2 will come, father in the middle. So, I write M, Fs and SFM because father is in the middle. Okay. Now, we are going to find the intersection. E intersection F is equal to, what are the members common? Same, MFS and SFM. These 2 are common. So, MFS comma SFM. Now, formula. P of E given F is equal to P of E intersection F divided by P of F. That is equal to. Now, see, total 6 outcomes. Of that, only 2 are possible. So, 2 by 6 divided by, what is probability of F? That is same, 2 by 6. So, what is the answer? It is 1. P of E given F, you get the answer as 1. Okay. So, these were the problems based on conditional probability. Simple type of question comes, sometimes it will be direct or you will have to select E and F. Now, let's move to the next topic. This is also a simple one. It's called multiplication theorem on probability. Okay, so what is a multiplication theorem? If E and F are two events of a random experiment with P of E greater than 0, probability of F is also greater than 0, then probability of E intersection F is equal to, that is probability that E and F takes place together. What is it? Probability of E into probability of F given E has taken place, that is same as probability of F into probability of E given F. If you take E, the second one will be F given E has taken place. So, if you start with F, second one is E given F has taken place. Now, let us see how we can derive this. We are familiar with the conditional probability P of E given F is equal to P of E intersection F divided by P of F. So, from here I can write P of E intersection F is equal to P of F into P of E given F. I will just name it as 1. Same way, P of F given E also has a formula, that is P of F intersection E divided by P of E. And from here, now F intersection E, intersection F both are same. So, I can write P of E intersection F is same as P of E into P of F given E, that I name as equation 2. So, combining these two, I can write P of E intersection F is equal to P of E into F given second has taken place, that is equal to probability of F into probability of E given F has taken place. So, when do you apply multiplication theorem on probability? If two events occurs together, simultaneous occurrence of event takes place, then we can apply multiplication theorem on probability. So, I can write P of E intersection F. Now, E intersection F, sometimes we write E F, both are same. Instead of writing E intersection F, I can write P of E F. So, how do I apply multiplication theorem? If E comes first, I can write probability of E into probability of second given first one has taken place. Okay, just imagine you have three events A, B and C. So, how do you write probability of A intersection B intersection C using multiplication theorem? Instead of this intersection, I can just write probability A, B, C. What does that mean? A, B and C takes place. This is same as, if you fix A, it is probability of A into first one into second one, probability of second given first has taken place, into probability of third given the first two, that is A, B has taken place. This is multiplication theorem. So, here I did for 2 events, it is 3 here. Now, if 4 comes, what will you do? If it is A, B, C, D, I will write probability of first into probability of the second given first has taken place, into probability of third given first 2 has taken place, into probability of the last one, the fourth one given the first 3 has occurred. So, like that you can expand this result to any number of events. Okay, so now let us see how we apply in problems, then it will be easy for you. Let us read this question. An urn contains 10 black and 5 white balls. 2 balls are drawn from the urn, one after the other without replacement. So, what is the experiment? You have an urn that contains how many? 10 black and 5 white balls. So, you have 10 black and 5 white balls, total 15 balls. Okay? 2 balls are taken, one after the other, without replacement. What do you mean by without replacement? When you pick a ball, you are not keeping it back. Okay, that's called without replacement. What is the probability that both drawn balls are black? So we need to find probability that first one is black, second one is also black. Here we can apply which theorem? Multiplication theorem. So when you apply the theorem, it's like probability of getting a black ball. First one is a black into probability of getting second one black given first has already taken place. Okay, that is equal to. Now tell me children, what is the probability of getting a black? Total 15 balls are there, 10 balls are black. So 10 by 15 into probability of again getting a black given the first one is a black. So here is it with replacement or without replacement? It is without replacement. That means earlier it was 10 black. Now it is 9 because one ball is already gone. 5 white and the number reduced to 14. So what will I write here? Total 9 balls are there which is black in color. 9 divided by 9 by the total is 14. So 2 5s are 10, 2 7. So your answer is 3 by 7. So when you simplify, you get the answer as 3 by 7. This is how we apply the multiplication theorem on probability. So it is without replacement, so there is a change in the probability. Now let's see one more question. 3 cards are drawn successively without, here also without replacement, you are not keeping it back, from a pack of 52 well shuffled cards. What is the probability that the first 2 cards are kings and the third card drawn is an ace? So total 3 cards you are going to take. First 2 are king and the third one is an ace. So you are going to find probability of king. First is a king, second is a king and the third one is an ace. Same multiplication theorem we can apply here. So when you apply the theorem, it is probability of getting a king in the first time into second is also a king given that first is a king into probability of getting an ace given the first 2 are kings. Okay. Now total 52 cards are there, 4 kings are there, 48 non-kings are there. How many aces are there? 4 aces present. Now let's fill it. What is the probability of getting a king in the first time? It is 4 out of the total 52. 4 by 52 into. Now, one card is gone. So, this 4 becomes 3. 48 remains 48. Okay. And there is a slight change. 52 becomes 51. Probability of again getting a king means 3 kings are left. So, 3 by the 50 total was 52. Now, it becomes 51 by 51 into. Next is probability of getting an ace. How many aces are there? 4 aces are present by. Now, one card is gone from here. So, it became 3. One more card is gone. So, now it is 2. So, what happens to the total? Total becomes 50 right now. So, by 50 because it is without replacement. So, it keeps changing. The denominator keeps on decreasing. That is equal to, now it get cancelled. 13, 17 will come here to 25. So, when you multiply, you will be getting 2 divided by 13 into 17 into 25, that is equal to 2 divided by 5, 5, 2, 5. So, when you simplify this, you will be getting 2 by 5, 5, 2, 5 and that is our answer. Okay, now hope you understood how to apply the multiplication theorem in probability. That is, if more than one events happen together, we can apply multiplication theorem. And then there is one more topic which is related to that, that's called dependent and independent events. That is, I'll just give you one example so that it will be clear to you. Suppose you have an urn that has, say, 6 red balls and 5 black balls, and then you are going to take 2 balls from there, one after the other. Okay. Now, let us take it as 2 cases, that is, one is with replacement, you are replacing, and the other one is without replacement, you are not keeping it back. Okay, with replacement and without replacement. So, my question is, if this is the case, that is, you are taking balls from here with replacement, what is the probability of getting a red ball? 6 red balls are the total, 6 plus 5, that is 11. So, I will write 6 by 11 here. Now, it is with replacement, okay, you are taking something, you are keeping it back. Now, what is the probability of again I will give R1 here, showing that first one is red. What is the probability of getting a red ball again, given that the first one is red? What happens here? What happens here? Is there any change in the probability? You took a red ball, you kept it back. Again, what is the probability of getting a red ball? Same thing, right? It is 6 by 11. There is no change. Same way, if I ask what is the probability of getting a red ball, given the first one is a black ball. You took a black ball, you kept it back. There is no change in the order. So, what is the probability of getting a red again? Same, right? It is 6 by 11. Even the first ball drawn is red or black, again the probability of getting a red again is not changing at all if it is with replacement. Now, let us see the case where it is without replacement. So, what is the probability of getting a red ball in the first attempt? It is 6 by 11. Now, what is the probability of again getting a red ball, given the first one is red? So, will there be any change in the probability here? Early it was 6 red, now it becomes 5 red, 5 black ball remains the same. So, from this collection, again getting a red means your answer will be 5 by 10. There is a change in the probability. But here, even if red is taken or black is taken, probability does not change. These sets of events are called independent events. Occurrence of one event is no way depending on the other. Now, these are called dependent events. One is depending on the other. So, there is a slight change in the probability. Now, if E and F are independent, then I can say probability of E given F is same as probability of E. There is no change, because even if F occurs or F does not occur, there is no change in the probability of E. Same way I can say probability of F given E will be same as probability of F. Whether E occurs or not, F's probability is not going to change if E and F are independent. Okay, and one more, we know probability of E given F, by definition it is P of E intersection F divided by P of F. So, what is P of E intersection F? That is equal to P of F into P of E given F. Suppose E and F are independent. So, instead of this I can write P of E. So, this is the condition to check whether two events are independent. What is the condition? If you can prove P of E intersection F is equal to P of E into P of F, then we can conclude those two events are independent. Otherwise, one will be depending on the other. Now, let us do one simple example based on that. A die is thrown. If E is the event, the number appearing is a multiple of 3 and F is the event, the number appearing is even. Then find whether E and F are independent. So, the condition we know P of E intersection F, if you can prove P of E into P of F, then we prove those two are independent. So, let us write the event E. The number appearing is a multiple of 3 when you throw a die. So, multiple of 3 means you have 3 and 6. And what is event F? The number appearing is even. So, you have 2, 4 and 6. We will find E intersection F also. What is a common element here? The common element is 6. Multiple of 3 and even number. So, that is 6. E intersection F is 6. Now, P of E intersection F. What is the answer? 1 out of the total 6. What is P of E? 2 members are there out of 6. And what is P of F? It is 3 by 6. Now, multiply and see. P of E into P of F is equal to 2 by 6 into 3 by 6. That is equal to 1 by 6. So, are we getting the same answer? Yes. P of E intersection F is P of E into P of F. So, these two events are independent events. Now, there are some properties based on that. The properties are, if E and F are independent, then the complements are also independent. That is, E complement and F complement are independent. Next one is, E and F complement are independent. E complement and F are also independent. Let us see how to prove this. So, given condition is E and F are independent. So, what does that mean? P of E intersection F is equal to P of E into P of F. So, we have this condition with us. Now, we are going to prove E complement and F complement are also independent. That is, if we can prove P of E complement intersection F complement is equal to P of E complement into P of F complement, then our proof is done. So, how to start? We start with the left side. P of E complement intersection F complement. What is this by definition? I can write this as E union F the whole complement. This is our De Morgan's law. We know A complement intersection B complement can be written as A union B complement. And this is equal to probability of E complement or probability of complement of an event is same as 1 minus probability of that event. So, this is E union F whole complement, which can be modified as P of E union B, 1 minus P of E union B. Now, we all know the formula of P of E union B. Just apply that, 1 minus P of E plus P of F minus P of E intersection F. Open the bracket, 1 minus P of E minus P of F plus P of E intersection F. That is equal to 1 minus P of E minus P of F. Now, look at this, children. E and F are independent. So, we know this condition. P of E intersection F is same as P of E into P of F. Now, we combine this. From these two, we will take minus P of F outside. This is 1 minus P of E minus P of F. I am going to take outside. This is combined. From there, I get 1 minus P of E. 1 minus P of E. So you have 1 minus P of E here, 1 minus P of E, which can be combined and you can take that outside into 1 minus P of F. Now what is this thing? 1 minus P of E is P of E complement into 1 minus P of F is P of F complement. So what did we prove? We proved if E and F are independent, then E complement and F complement is also independent. Just start with the left side, apply De Morgan's law, and then 1 minus P of E union B, apply the property of union of two events, and then finally you will get the right side. If E and F are independent, E complement and F complement are also independent. Now one more part is there, that is if E and F are independent, then I can prove E and F complement are independent. Same way E complement and F are also independent. So I will show you the first proof. Similarly you can prove the next one also. For this I will just take the help of Venn diagram. I have events E and F. So what is the name of this region alone? It is E intersection F complement. This region is called E intersection F, and this one is called F intersection E complement. Okay, so I am just going to prove E and F complement are independent. From the figure, children, I have three disjoint regions. One is E intersection F complement, the other one is E intersection F, and the third one is F intersection E complement. Now from the figure, I am going to write E as the union of these two regions. Which all regions? E intersection F complement union E intersection F. And then I am going to find the probability on both sides. Probability of E is equal to probability of E intersection F dash union E intersection F. That is equal to probability of A union B formula, P of first one plus P of the second one. Now what about the third thing, minus P of intersection of these two? Will that part exist? No, because these two are disjoint regions, so intersection is empty. So probability will be 0, so we just have two terms. Now we'll keep it here and take the remaining things to the other side. So I can modify this as P of E intersection F complement is equal to P of E minus P of E intersection F. E and F are independent, so you can break it. This is same as P of E minus P of E into P of F. Now what is common here? P of E is common. That is equal to, I took P of E outside, in brackets I get 1 minus P of F. Now what is 1 minus P of F? It is P of F complement. So what did we get? The left side was P of E intersection F complement equal to. Now I get P of E into. Now when you combine this 1 minus P of F, I will get P of F complement. So what does this mean? If E and F are independent, E and F complement are independent. Same way you can prove E complement and F are also independent by taking the other side. Here I took E as union of two regions. Same way you can take F as a union of these two regions and you will get the same conclusion. So always remember, if E and F are independent, then the complements are independent, then E complement and F are independent, F complement and E are also independent. That is a proof. Now we will do one example. Two cards are drawn at random and without replacement from a pack of 52 cards. Find the probability that both the cards are black. It's a combination of multiplication theorem, and in between independent events and dependent events, such questions also comes. So, what is the probability that both cards are black? So, this is our multiplication theorem only. Probability of getting first one black, second one black. It is without replacement. So, when you take it, you are not keeping it back. So, when we apply the theorem, we get probability of B1 into probability of B2 given the first one is a black. So, this is equal to. So, how many black cards are there, children? There are 26. There are 26 black cards. So, out of 52. So, 26 by 52 into. One card is already taken. So, out of this 20, now 26 becomes 25. 52 becomes 51. Again getting a black means what will we write here? It is 25 divided by 51. Okay. So, this get cancelled, 2 will come equal to 25 by 102. So, your answer is 25 by 102, which is a very simple question. Just apply the multiplication theorem and then you simplify your answer. Next one, a box of oranges is inspected by examining 3 randomly selected oranges drawn without replacement. If all the oranges are good, the box is approved for sale, otherwise it is rejected. Find the probability that a box containing 15 oranges, out of which 12 are good and 3 are bad ones, will be approved for sale. So, what is the experiment here? 3 oranges are taken. If all these 3 are good, then that box is approved for sale. So, we need to get, and the question is, find the probability that the box containing 15 oranges, out of which 12 are good and 3 are bad ones, will be approved for sale. So, will be approved for sale means those 3 oranges that you selected, they are good ones. So, we need to find probability of G, all 3 are good. First is good, second and third one is also good. So, what is it? If I write 1, 2, 3, I can write probability of first into second given first one has occurred into probability of third given the first 2 has taken place. That is equal to. Now, what is the probability of getting a good one? It is 12 by 15. 12 good ones are there out of total 15, isn't it? So, 12 by 15 into. It is without replacement. So, it's not, we are not keeping it back. Again getting a good one means, what is it? There is a change. 12 becomes 11, 14 into. Again getting a good one means it becomes 10 divided by 13. So, when you cancel, what will you get? 15. So, that is equal to 2 into 2, 4. 44 comes in the numerator by, so you get 91. So, your answer is 44 divided by 91. Okay. So, this is a simple application of multiplication theorem on probability. Next question. 2 balls are drawn at random with replacement from a box containing 10 black and 8 red balls. It is with replacement. So, whatever you take, you keep it back. Find the probability that first one, both balls are red. Second one, first ball is black, second is red. And the third one of them is black and the other is red. So, let us do the first one. The first one is both balls are red. So, I need to find probability of both are red. First is red, second one is also red. Now, total how many are there? There are 18 balls in total. you have 10 black balls, 8 red balls, okay, and whatever you are taking, you are keeping it back. So, probability of getting first red, what is it? 8 by 18 into, when you apply the theorem, again getting a red given that the first one is a red. So, there is no change, it is 8 by 18 only. Okay. So, when you simplify it, what will you get? This is equal to 16 divided by 81. Okay. The first one is 16 by 81. Now, let us see the second one. First ball is black and the second one is red. So, the second one I can say probability of first is black and the second one is red. So, when you apply, first one is black. So, total how many blacks are there? 10 blacks are there out of 18. So, 10 by 18 into getting a red ball again given that the first one is a black. So, if it is with replacement, so nothing, in the denominator the number is not going to change. So, again getting a red ball means how many red balls are there? There are 8 red balls out of 18. So, 8 by 18. So, that is equal to, so when you simplify it, two fours are 8, you get 20 by 81. Okay, second one's answer is 20 divided by 81. Now, let us see the next one. One of them is black and the other is red. So, one of them is black and the other is red. So, what are the possibilities? It can be first one is black, the second one is red, or first is a red one and the second one is a black one. Okay, I can give like this. First is black, second is red, or first is red, second is black. That is equal to probability of first is black and the second is red, already we have here, that is 20 by 81, we know the answer. So, first is black, second is red, plus probability first is red, second is black. So, what will be that? It will be like 20 by 81 plus 20 by 81 will come. So, 20 by 81 plus 20 by 81, that is equal to 40 divided by 81. That is the answer, 40 by 81. Next question. The probability of solving specific problem independently by A and B are 1 by 2 and 1 by 3 respectively. If both try to solve the problem independently, it said independently, find the probability that the first one is the problem is solved. Second one is exactly one of them solves the problem. So, hope you understood the meaning. There are two people are there, A and B, and they are going to solve a problem. So, and they are solving it independently. So, what are the possibilities? Like both can solve, both will not solve. If A solves, B does not, and if A does not, B solves. So, these are the possibilities. Total 4 possibilities are there. And it is given that probability of A solving the problem is 1 by 2. And B solving the problem is 1 by 3. Okay. So, if solving the problem is 1 by 2, let us find A complement also. What is that? 1 minus 1 by 2, which is 1 by 2. And probability of B complement, what is it? That is equal to 1 minus 1 by 3, that is equal to 2 by 3. So, we just keep the complements also ready. Now, let us try to answer the first one. Find the probability that the problem is solved. So, is solved means one or both can solve the problem. So, that means this case can come, this case can come. Okay? 3 cases can arise, and we know total probability is 1. So, instead of adding all these, it is enough to find. Now, only one case is left here, no. It is enough to find, that is the first one. It is enough to find 1 minus probability, none of them solves the problem. Isn't it? So, the correct answer is probability of A intersection B or A intersection B complement or A complement intersection B. Instead, I can write, since total probability is 1, probability that the problem is solved is same as 1 minus probability none of them solves the problem, because only one case is left here. So, how do you write this? This is same as 1 minus P of A complement intersection B complement, and you know A and B are independent. So, we proved the complements are also independent. So, you can split this. This is same as P of A complement into P of B complement. Now, the complement values are ready here. 1 minus 1 by 2 into 2 by 3. That is equal to 1 minus 1 by 3. So, the answer is 2 by 3. So, this is the answer for the first part. Probability that the problem is solved. What about the next one? Exactly one of them solves. Exactly one of them solves means the last two. If A solve, B does not, and if A does not, B does. That is a case which we are going to consider. So, to prove the second one, probability exactly one solves is same as probability A does not, probability A does not and B solves, or A solves and B does not, which is same as P of A complement intersection B plus P of A intersection B. Why are we adding? Because these two are disjoint, so intersection is empty. Now, A and B are independent, so A complement and B are also independent. So, I can apply the property plus probability of A into probability of B complement. All the values are available here. So, the values are available here. P of A is 1 by 2, A complement is 1 by 2, P of B is 1 by 3, B complement is 2 by 3. So, let us substitute here. This is equal to P of A complement. So, what is P of A complement's value? P of A complement is 1 by 2. So, we will substitute 1 by 2 there. 1 by 2 into. Now, P of B. What is the value of P of B? P of B is 1 by 3. So, 1 by 3 plus P of A is 1 by 2. And P of B complement is 2 by 3. So, just find the answer. 1 by 6 plus 2 by 6, that is equal to 3 by 6. So, the answer is 1 by 2. So, the answer is 1 by 2 for the second case. So, children, with this we come to an end of the session. So, what all things we discussed today? That is the first portion regarding conditional probability, and then we discuss few simple properties based on conditional probability, multiplication theorem on probability, and then a topic called dependent and independent events. What is the conditions based on that? When do you say two events are dependent and independent? All these we discuss. Hope that is clear to all of you. Thank you.